So in part one, we finished getting introduced to the different types of electromagnetic radiation. Some are dangerous, some are not. So let's kind of review what they are and talk about why. So we got not dangerous, dangerous stuff. So what's not dangerous include radio waves, microwaves, infrared light, and visible light. So those are the low energy, big wavelength electromagnetic radiations. Dangerous stuff, obviously, then are the other three: ultraviolet, X-rays, and gamma rays. So why are some dangerous? Why are others not? So dangerous types of radiation are called ionizing radiation. They possess enough energy to remove electrons. If you take an electron away, what do? You create an ion. You've ionized the atom. So they have enough energy to remove electrons from the electron cloud and to even break bonds of the molecules in our body. So as a result, we can suffer injury. Small exposures to radiation can usually be handled by our body. We can usually fix anything if a cell dies or if we get a DNA damaged a little bit. We can often fix that stuff. It's large doses that we have to really worry about as far as dangerous types goes. Those are the things that can lead to tumors and obviously death, ultimately, if you're exposed to huge quantities of radiation. As opposed to the non-ionizing radiation, the non-dangerous stuff. So what they do is they don't have enough energy to actually remove an electron or break bonds. What they do is they just cause the molecules to vibrate. So that's how, like I said, that's how a microwave works. It causes water molecules to vibrate and increase in temperature, but not destroy the water molecule itself. All right, so last thing we want to do is get an understanding of the quantitative relationships between energy, wavelength, and frequency. So if you remember, we went through that big diagram, noticing hopefully a few things. Energy and wavelength have an inverse relationship. So as the wavelength gets bigger, the energy gets smaller. Energy and frequency have a direct relationship. As you increase the number of waves passing a given point, more energy is associated with that. And then the inverse relationship between frequency and wavelength, as the wavelength gets bigger, fewer waves pass a given point. So frequency gets smaller. So let's take a look at the equations that are associated with these relationships. The first one sets the relationship between wavelength and frequency. You multiply wavelength times frequency, so as one gets bigger, the other gets smaller. They are always still constantly traveling at the speed of light. So wavelength times frequency is equal to the speed of light. Here's an example of a question. So a green light on a traffic signal has a wavelength of about 522 nanometers. What's that frequency? Well, you can look at the equation that I've got here. So I'm going to take C equals lambda nu and rearrange it. Remember, that's what I want you to learn how to do. I want you to learn how to rearrange equations rather than just plug the numbers in and rearrange it with the numbers. It's much easier to rearrange these variables than it is to have to rearrange these numbers. Oops. Sorry about that. So let's just take a look and see how the units are working out here. You've got 3 times 10 to the 8 meters per second is the speed of light. You're dividing that by nanometers, okay? Well, that's not going to work. So transfer that into meters from nanometers. 1 times 10 to the 9 nanometers per meter. Gives you meters, wind up canceling out. You're left with per second, which is frequency. The other relationship is getting energy in there. In order to do energy, we need to throw in another constant. We need to put in something called Planck's constant. That's what accounts for the idea of the photon. Planck's constant takes into account that you need a certain quantity of energy to accomplish anything. So Planck's constant is really accounting for the photon property of electromagnetic radiation. So the energy is equal to Planck's constant times frequency, or energy is equal to Planck's constant times frequency, or times speed of light divided by wavelength. So notice that frequency is equal to speed of light divided by wavelength. So we're just substituting one side of the previous equation for the other. All right, so here's the last example of that. Calculate the energy in joules of a photon with a wavelength of 5 × 10 to the 14 nanometers. So you've got wavelength, you need energy, so this version of the equation is what you can use. So wavelength is 5 × 10 to the 4 nanometers. I can convert that into meters. And then Planck's constant, 6.63 × 10 to the negative 34, and the speed of light, 3 × 10 to the 8 meters per second. You get an answer in joules, although this is not right. I'm pretty sure this answer is right, but I think I just typed this wrong. Sorry about that. Go ahead, check me, make sure. And that is actually the last of the videos. So you've got some qualitative stuff to work with, you got some quantitative stuff to work with. After watching these two videos, there's a few problem sets that you need to do. Please do check your assignment sheet for that assignment.